Well guys, let's solve these three limits right here, but without evaluation. We need to figure out if these limits tend to infinity or 0, but without evaluating these limits. So, to evaluate such limits, as you can see that here they're either in 0 or infinity form, and we can just simply evaluate them by using L'Hospital's rule. But let's not do that either. Let's just not use any limit method at first, and let's evaluate them. Now, what we do here for these limits is we kind of just check and plug some numbers, and we have to compare the numbers for the numerator and denominator because they are each of their own functions. So essentially we have to just measure their rate of growth. So rate, that means derivatives. And in fact we can solve them by doing the derivatives of the numerator and of the denominator, which is just L'Hospital's rule. But as I said earlier, we're not going to do that. So for the first limit, you have to see here that x cubed is much greater than x squared. And here x tends to 0. So let's just put in a number. Let's say 0.1. So when you square that, you multiply it by itself, 0.1. And here this is just 0.01. Now what if you do cube? X cubed, 0.1 cube. Well, you have to multiply it by 0.1 here. So you get 0.001. And as you can see, 0.001 is obviously lesser than 0.01. And when these numbers get smaller and smaller, this number will be far smaller than this number, meaning that this whole limit will in fact just be 0. And to solve this limit, what you have to do is you can use L'Hospital's rule. So if you use L'Hospital's rule, this will first be 3x squared plus 3 by this will be 2x plus 98, and again just use the L'Hospital's rule. So above you'll get 6x and down you'll get 2, and as x tends to 0, this will just be 0. So for the second limit, we have ln x by e to the power x as x tends to infinity. Now ln on infinity is infinity, e to the power infinity is also infinity. So without evaluation, I think this is kind of easy, because when you take log of a number, you reduce that number by so much. But this is an exponential function. An exponential function, the graph is like this, so that means the number will rise very much for bigger numbers. So let's take a number, for example. Let's take ln of, let's say, 1000, and this will be approximately, let me check, 6.9. But what if you take e to the power 1000? Well, e to the power 1000, we don't need to have to calculate that. By logic, we know that this will be far greater than 6.9. So that means when x tends to infinity or to a much greater number, this limit will obviously be 0. And to check that, you can also take L'Hospital's limit right here, or use L'Hospital's rule. So this will become 1 by x by e to the power x, and if you plug infinity, well, this is first x into e to the power x, and as you can see we'll have 1 by infinity, which is 0. Now time for this limit right here, which is a bit difficult to calculate because we have exponential function as well as factorial, which both produce great numbers for large numbers. So let's just take this limit over here. Now we do not want to evaluate this limit, but let's look at some observations. So let's look at this factorial one, because with x to the power x we cannot really do anything, but x factorial, what is this equal to? Well, x factorial is just x into x minus 1 into x minus 2 into x minus 3 and all the way to 1. Let's see how many terms x factorial contains. As I mentioned earlier, x factorial is x into x minus 1 into x minus 2 all the way to 2 into 1, but we can just ignore that 1 and say x factorial has x minus 1 terms. And right here, x factorial. If instead of x minus 1 we write x, and instead of x minus 2 we write x, well, this number, this will in fact be lesser than x into x, because we replaced a smaller number by a bigger number. So that means this number will in fact be lesser than this. So I'm going to write it right here, x into x dot 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 and x right here. So in fact, how many terms does this also have? Well, if this has x minus 1 terms, and for each of the numbers we replace it with x, that means this also has x minus 1 terms. So that means we multiplied x with itself x minus 1 terms, or x minus 1 times. So in fact, x factorial is lesser than or equals to x to the power x minus 1, because of the fact that x factorial can be equal to x to the power x minus 1 when x is equal to 1. So we have to put this equal to sign over here, and this is what we need. But we also need something else. For the squeeze theorem to work, we need a function in the middle, and here we need it to be in between of two inequalities over here, a and b, like this. Evaluate the limit and use the squeeze theorem. Well, we have found one over here, we have found this, but what about this? Well, to find this we have to know some things about x factorial, or not things, just one thing. We have to see what is the smallest number x can be. Well, by definition, this x has to be an integer. The smallest number it can be is 0. And right here, 0 factorial is equal to 1. So that is this. X factorial is lesser than or equal to 1. So we have to continue from here, and let me just make this a bit nicer. From here, we want x to the power x by x factorial. And for the squeeze theorem to work, we need to work with this, and right here we want it to be in a denominator. What you can do is just take the reciprocal. When you take the reciprocal of any inequality, this sign flips. So this is 1 by 1, which is just 1. This will now be greater than or equal to 1 by x factorial. This will be greater than or equal to 1 by x to the power x minus 1. Now we want x to the power x, multiply both sides by x to the power x. So you get x to the power x greater than or equal to x to the power x by x factorial greater than or equal to x to the power x by x to the power x minus 1. And now in the next step we need to take the limit. So let's take each of these limits as x tends to infinity. So x tends to infinity, x to the power x greater than or equal to x limit infinity, x to the power x by x factorial greater than or equal to x limit infinity. And right here, x to the power x by x to the power x minus 1. We can somehow simplify that, right? Well, x to the power x minus 1 is just x to the power x into x to the power minus 1. And this is just 1 by x. We in fact have x to the power x by x to the power x into 1 by x. So that means this and that will cancel, and this x will go above and we'll have x. So this is just x right here, and put in the limit for this and that. This will obviously be infinity, and that will also be infinity. And right here, as you can see, for the left inequality we have infinity, and sorry, I forgot the inequality for here. And for the right we also have infinity. And by the squeeze theorem, when this is equal, that must mean that this limit over here, x to the power x by x factorial, this will in fact have to be infinity. And there we go, we proved it. So if you guys done something new, just like and subscribe. Thank you.